Okay, now we are doing lecture 4. Lecture 4 is about mixed strategy. So far, we've learned what is the IESDS and what is the Nash equilibrium. But when we are looking for predictions or future behavior, we usually were based on so-called pure strategy equilibrium. I'm going to explain later what is the pure strategy equilibrium. And also there is mixed strategy. Those are different. So first, think about a penalty kick game. Penalty kick game is a virtual game where there are two players, goalkeeper and kicker. So, ball kicker will kick the ball, but kicker will kick the ball, but goalkeeper will defend the ball. There are many strategies in real. We just assume that kicker will decide which direction um, he will kick the ball between left side or right side. And also goalkeeper only can defend the ball from the left side or right side. Because usually the speed of a ball is so fast so that it's impossible for the ball keeper to decide to defend the direction after observing goal kickers where goal kicker is kicking the ball. Okay, so it's like there are two players here, goalkeeper and kicker. So these are the players. And also their strategy is the kicking the ball and defend the ball left or right. For example, if the ball kicker kick the ball to the left side, but the goalkeeper is defending the ball to the right side, then goal kicker will win. So that is a kind of penalty kick game. I just made it. So then think about this game. In this case, this strategy, kicking the ball left or kicking the ball to the right, we call that strategy pure strategy. Pure strategy. As you can expect, the pure strategy is the real strategy you can choose wholly. In this case, kicking the ball to the left or to the right, that is the pure strategy. And also we have mixed strategy. Mixed strategy is something you can choose the strategy in this example to the left or right randomly. Where is the random? We don't have a randomness here. However, think about a kind of machine. This machine gives you a number, for example, 0 to 1. And if this machine gives you 1, you are supposed to kick the ball to the right or defend the ball to the right. And also, if this machine gives you 0, then you are supposed to go to the left and kick the ball to the left, or if you were goalkeeper, you are going to defend the ball to the left, not right, left. So you don't have any willingness which direction you are going to kick or defend the ball. Just you are following the number machine will give you. That is the way of making a mixed strategy. But when the machine gives you the number, it follows probability. For example, this machine has its own distribution. For example, giving number 1 with 70%, and the other 30% it will um, give 0. But it will be given randomly. You don't know which number will be given to you. Only what you know is that its distribution, like the probability, 70% or 30%, something like that. Once the machine gives you a number, then you will follow that. There is no your willingness at all. You are just following. I mean, in this sense, you can mix strategies between left or right. That is called mixed strategy. Compared to the pure strategy, in this case, there is no mixing. You are choosing left or right. That is the pure strategy. But the mixed strategy, like you are, mixing right with the 70% and left with 30%. That is the mixed strategy. Okay? For example, we can represent the mixed strategy in this sense. Let P is the probability of choosing right. That is P. So this P will be in 0 to 1. Okay? Then a mixed strategy, mixing the strategy left and right, will be represented by, in this sense, left times 1 minus p, because p is the probability of choosing all. So plus right times p. So this is a kind of way of representing a mixed strategy. Okay? Okay, now we have a normal form game, an arbitrary normal form game. You need to confirm that this is also normal form game. There are two players, A and B, and they can choose their strategies, D or C, and they will have some payoff depending on what strategy profile is chosen by players. And also we assume that implicitly these players choose their strategy simultaneously. So when they are choosing a strategy, they are not supposed to know what kind of strategy others will choose. That's the basic meaning of simultaneous. So anyway, so that this is a normal form game, let's find an equilibrium. First way we can try is to apply IESDS. IESDS. To find an IESDS, we need to find whether there is a dominating or dominated strategy. Look at the first player A. If the player B is choosing D, probably this player will choose C. However, if the player B is choosing C, then the player A will choose D. So there is no dominance between those two strategies. Look at the player B. If the first player is choosing D, then the player B will choose D. But if the first player choosing C, then the player will choose C. So there is no dominance as well. So that we cannot apply IESDS. Actually, we can apply it, but it means all the equilibrium, all the strategy profile will be survived from this process of IESDS. So that all strategy profile will be an equilibrium survived from IESDS. Now, what we can try is Nash equilibrium. So let's try Nash equilibrium. Nash equilibrium. So from the first player A, if the second player is choosing D, this player will choose this. When C, A will choose D. When A, this player will choose D. When C, then this player will choose this one. It's like there is no dominance. There is no Nash equilibrium, right? So as you can see, there is no Nash equilibrium as well. But actually, in this case, even though I'm saying there is no Nash equilibrium, but in terms of pure strategy, we haven't checked on the possibility that there is a Nash equilibrium with using a mixed strategy. Okay, so now we are checking whether there is a mixed Nash equilibrium. To do that, let's think about this. First, if player A is mixing, because we don't see any pure strategy Nash equilibrium, so that we try to find a mixed strategy Nash equilibrium. So, for example, let's check this. If player A is mixing D with 75% and C with 25%, think about this. 75%, it's like there is a machine which gives you D with 75%, which means if you are trying this game 4 times, maybe once among 4 times, you will choose D. In terms of probability, it's likely to choose D with 75%. Okay, so let's check what is the payoff in that case. So it's like you are drawing another row here, so that is 75D plus 25% of C. In that case, let's check the expected payoff of the player A and B. So we are making all the row here. Okay, in that case, that is 3/4 times D50 plus 1/4 times 90. That is 150, 240, so that's 60. Also, we can calculate, this payoff is the payoff when the second player B chooses D. In that case, also we can calculate player B's payoff, like 50 times 3/4 plus 10 times 1/4. That is, denominator is 4, numerator is 150, 160. So that is 40. So this column actually will have 60 and 40. Likewise, we can calculate this payoff when the player B chooses C and the player A chooses 75% of D plus 25% of C. What does it mean? Mixing 75% C and 25% of C. So what does it mean of the expected payoff? At the end of the day, if you look at the numbers, what you will get will be, I mean, from the A's view, what you will really receive is 50 or 90, right? That's, I mean, realized number. However, before knowing what kind of result you will receive, you can expect between, I mean, regarding these outcomes. It's like a 75%, I mean, 50, you will receive 50, with 25%, you will receive 90. So that if we calculate expected payout, that will be, as you can see, 60. And for the player B is 40, right? Also, we can generalize this idea. Here, I mean, 75% is just one probability, but depending on this probability, we may generalize what kind of payout each player will have depending on mixing. Okay, so let's think about this again. This time, let P is the probability of choosing D. So when P equals 1, it means the player A is choosing D. When P equals 0, then player A is choosing C. So in the middle, this player is mixing. So we can represent that like this. D, P plus C 1 minus P. That is the mixing of the strategy D and strategy C. That's what this player is doing. This player is mixing these two strategies. In that case, we can calculate this and this, right? However, this time, let's focus on player B's action or perspective. If player A is mixing D and C with probability P, then the expected payout that player B can get is something different. For example, I'm not talking about the player A, I'm talking about player B. When the player A is mixing these two strategies, the payout that the player B can get is, when player B is choosing D, 50 P plus 10 times 1 minus P. If a player B is choosing D, if we simplify this, then it was 10 minus 4 plus 40P. So this area, this payout, expected payout is 10 plus 40P, right? And also we can calculate this payout. I'm talking about, again, player B's payout. I'm not talking about player A's payout. I will talk why I'm calculating this. So again, if the player B is choosing C, then the player B's expected payout is that 20P plus 80 1 minus P. So there is 80 times 60P. That is the payout that this second player B can get when he is choosing D or C. So that is the payout that player B can get. But what it means, depending on the probability P, sometimes, I mean, choosing D gives B better payoff, or depending on the P, I mean, choosing C gives higher payoff to the player B. And we can find when these payoffs are the same. By solving this, AD minus 60p, if I'm moving this term to the left-hand side, this is 100p, and this is 70, and p equals 0.7. So again, some cases when p, some cases choosing D is better. In some cases, choosing C is better. But when the probability goes to 0.7, then, I mean, between these two strategies, there is no differences, right? I can describe this by drawing a graph. So I'm drawing this again as a graph here. So 10 plus 40p is here, depending on the p. This is 10 plus 40p. 80 minus 6p is this. Okay? This one is the expected payoff. So this one is the expected payoff when the second player is choosing D, and this is the expected payoff when the second player is choosing C. As we can see, when the probability of the first player, player A, of choosing D is less than 70%, then C is better. Because, we assume that players are sufficient rational, and when the P is less than 0.7, choosing C gives the second player higher payoff, right? But when the probability of choosing D of the first player is greater than 0.7, then choosing D gives the higher payoff per the second player, right? Right? Again, this is a payoff. It's actually expected payoff depending on the first player's probability of choosing the strategy D. Okay? So depending on the P, so if I'm summarizing this whole idea, right, I can summarize it in this sense, like this. When the probability is less than, from the player B's perspective, if the probability is less than 0.7, what is P? P is the probability of the player A to choose strategy D. Actually, DL it's the same thing, D. So if that probability is less than 0.7, then the second player is supposed to choose C, or Q equals C. I'm not talking about Q. Again, if the probability is greater than 0.7, then B is supposed to choose D. We can derive that from previous responses and payoff. Again, if the probability of choosing D of the first player A equals to 0.7, then there is no difference between choosing B and D and C. No difference, right? Actually, this is talking about best response. of the player B, depending on the probability, depending on P. So now, I mean, in the same sense, we also player B can mix. Let's say that Q is the probability of choosing D from the second player B's perspective. Again, why is the P? P is the probability of choosing D of the player A, and Q is the probability of choosing D from second player. Okay, those are different. Okay, so Q is the probability of choosing D, and let P be the probability of choosing D of the first player A. So in that case, choosing C from the player B can be represented by Q equals 0, because we define Q is the probability of choosing D of the second player B. Likewise, choosing D, forget about this, the second character CL, just CD. So choosing C can be represented by, Q equals to 1, because again, Q is the probability of choosing D of the second player B. Okay? So now, that is, if we look at this relationship, again, this is the best response from the second player B depending on the first player A. Okay? Likewise, we can find first player's best response function. Okay? We can do that again. In this case, it's more familiar with to use some other things. So now I'm going to type something. Okay, think about the second player. This is D, C, D, C, D, C, 50, 50, 90, 10, 80, 20, 20, 80. Pretty much what I did is to find the best response function of the player B. Now I'm looking for the best response function of the player A. Again, let Q be the probability of choosing D for the player B. So this is A, B. Now player B is player B is mixing its strategy. So in that case, if A chooses D, then what the expected payout is this one, choosing D. Expected payout is, because the player B is mixing D and C, so that 50Q plus 80 times 1 minus Q. That is 80 minus 30Q. Likewise, if A chooses C, then the expected payout is 90Q plus 20 times 1 minus Q. That's 20 plus 70Q. Right? So from the player A's perspective, if this expected payout is greater than this, then the player A will choose D, right? So if AD minus 30Q greater than equal to 20 plus 70Q, then the player, the A, will choose D. And this equation inequality will be simplified as this: 60 less than equal to 100Q. Therefore, it turns out if Q is less than or equal to 0.6, then A will choose D. We can represent that as P, or P equals to 1, right? Because what was the P? P was the probability of choosing D for the player A. Okay, what it means, if Q is greater than 0.6, then A will choose C, or P equals 0. Okay, so that is the best response for the first player, right? When the Q is less than 0.6, then P equals 1. Q is greater than 0.6, then P equals 0. And if the Q equals to 0.6, then there is no indifferent. I mean, we can represent it in this way. If Q equals 0.6, then there is no indifference between choosing D and C. It will be represented by this. P will be any number in 0.1. Okay? It means P can be any number in this interval, because for the player A, there's no difference between choosing D and C if the Q equals to 0.6. Okay? Now, going back to the slides. So that is this. When the Q is less than 0.6, then player A will choose D. It means P equals 1. And Q is greater than 0.6, then P equals to 0. That is the best response. I mean, what is the best response? Going back to this table. If we look at this table, what is the best response? This is the best response, okay? From the player A's view, player B is choosing D, then I'm going to choose C. If you are choosing C, I'm going to choose D. From A's perspective, from B's perspective, if you are choosing D, I'm going to choosing D. If you are choosing C, I'm going to choosing C. This underline actually representing the best response. This is the best response of the player A depending on player B's strategy, and this is the best response of the player B depending on player A's perspective, A's strategy. That's the best response. Okay? Again, in that sense, this is the best response, right? So, I mean, as before, we did write underline in the table. We can express this best response in a space which is representing each player's strategy. I mean, P can be changed from 0 to 1, and also Q can be changed from 0 to 1, right? And P is the probability of the first player's strategy of choosing D. Q is the probability of choosing D of the second player. So this means P equals 1. This means that player A is choosing D. This means that player A is choosing C. Here, this corner represents player A is choosing C and player B is choosing D. And this corner is representing both player choose CC. This represent both player choose DD. And this is that first player is choosing D, second player is choosing C. So those four corners are representing pure strategy profile. All the other areas are mixed strategy profile. Okay? Okay. Now let's representing previous best response function here. I mean, this is the best response. If the P is less than 0.7, then Q equals 0, 0. Okay? If P is less than 0.7, then Q equals 0. So that this horizontal line from here to here is representing this best response. If P is greater than 0.7, then Q equals to 1. If P is greater than 0.7, then Q equals 1, right? And look at this. When P equals 0.7, then Q will be any number. Q will be any number in 0, 1, right? So when P equals 0.7, Q will be any number. So these lines represent the best response for the second player's best response line. Likewise, we can draw first player's best response. Going back to the previous slide, when Q is less than 0.6, then P equals 1. When Q is less than 0.6, then P equals 1. When P is greater than 0.6, then P equals 0. P equals 0. When PQ equals 0.6, it can be any number. When Q equals 0.6, P will be any number in 0 to 1. So this blue line represents first player's best response. Now I'm arguing here this point. This point can be represented 0.7 D plus 0.3 C, comma. This is the first player's strategy, mixed strategy, and 0.6 D plus 0.4 C. This is the second player's mixed strategy. Okay? I mean, this point is representing this because two players are mixing. And I'm arguing that this is the Nash equilibrium. I spent a lot of time to explain this. Finally, I'm arguing that this is the Nash equilibrium. Think about it. As long as from the first player's view, this is the first player's best response function. If you are playing this strategy, the second player is playing this strategy, right? This strategy means this. To me, I have any strategy, any mixed strategies give me the same payoff so that I don't have any reason to deviate from current mixed strategy for me. Say again, If the second player is playing this game, this strategy, I don't have any reason to change my behavior, because even though I'm changing my strategy all the time, it gives me the same problem, um, same payout. Okay, let's check it whether it is true. If the second player is mixing 60%, second player is mixing with 60% and 40%, right? If I'm playing, in that case, if I'm choosing D, my payout is 50 times 0.6 plus 80 times 0.4. That is 30 plus 24, 32. So this is 62. If I'm choosing C, 90 times 0.6 plus 20 times 0.4. This is 64, this is 8. So that this is 62. As we can see, if the second player is mixing D with 60% and C with 40%, I mean, even though I'm choosing D or C, my payoff is the same, 62. So in my case, no matter what kind of mixing strategy I'm choosing, I mean, my payoff is the same. Okay? So if the second player is mixing with 60 percent for the playing D, I mean, from my perspective, currently I'm choosing this strategy here, but even though I'm changing my mind, it does not give me any better payoff. So I don't have any reason to change my mind. So I'm staying here. Likewise, if I'm staying in this strategy, right, then no matter what kind of mixing the second player is choosing, its payoff is the same. So that the second player does not have any incentive to change its strategy from the current mixed strategy. So that this point is the mixed strategy Nash equilibrium, because no one has an incentive to deviate. But now, look at other one. How about this? Is a Nash equilibrium? I don't think so. If you are mixing this, so from my perspective, from the first player's perspective, it does not give any incentive to change my mind. So I just pick up this one. Okay. Then, if I'm mixing certain, say that this is 0.3, I'm playing, so this, just say that this is a 0.3D plus 0.7C. So I'm mixing in that, in this sense. I mean the first player. From the, now look at the second player's perspective. If we look at second player's perspective, then this is the best response function. If we are mixing in this sense, the second player choose C. Not anyone. It should choose C. Okay? I mean, when the second player was mixing with 60% for the strategy D, in that case, there's no differences for the first player. But here, if the first player is playing this strategy, then the second player has an incentive to play C. If the second player is playing this one, then all the time first player is playing this. Okay, if the first player is choosing this, then second player is choosing this. Again, if the second player is choosing this, then the first player is choosing this one. It's circulating. So no Nash equilibrium can be found here. No stable equilibrium can be found here. What it means, this one is the only unique Nash equilibrium. Actually, this is the mixed strategy Nash equilibrium. Okay? You may not understand quite well at this moment, so I hope you just stop here and just try to redo again everything. That it will be very helpful. Okay, and you should understand that very clearly and correctly. And I hope you do this exercise. Everything is the same, but it's a little bit different. I mean, find all equilibria, including pure strategy, Nash equilibrium, and mixed strategy, Nash equilibrium. You should find everything. I mean, if I'm giving you a hint, there are 3 equilibria, 2 strategy, Nash equilibrium, and 1 mixed strategy, Nash equilibrium. Try to find it. Okay, now I'm stopping here.